Let's talk about 7.3, the central limit theorem with proportions. Now, we've already been using the central limit theorem to find probabilities for sample means, but now we're going to use it for finding probabilities of a sample proportion. Now, the word proportion may seem a little bit different because we haven't really used that word too much yet. So let's talk about what we mean by a proportion. So a proportion, in preference to a population first, a population proportion is basically given by P equals X over N, and that's a capital N there, which is going to be a little different. So X is again the number of individuals in a population that have a certain characteristic, and N, capital N there, is the size of a population. Now with most problems when we talk about this, if it is a word problem, we do normally give this as a percentage. It's not normally given in a fraction, so you're not going to see a fraction. So they'll either say like that this many people out of this many in the population meet this requirement, and then you have to create that fraction, or it will be given as a percentage. So a lot of times you'll see like something like, let's see, P is 51%. Now, when I start to do my calculator stuff, I have to remind myself, okay, well, that's 0.51, or I can also remind myself that that is 51 over 100. Okay, so again, this is kind of where it's a proportion of a population itself, and we're just going to use P to represent proportion here. Now, when I start talking about a sample proportion, I'm going to call it P hat. Now, remind yourself back to the stuff that we were looking at in previous sections. We were letting mean be our population mean using that mu symbol there, and we were using X bar as our sample mean. Okay, now we have added in that if we're referring to the sample mean itself, we kind of say mu of the X bar itself, because that was the notation that we started to use in chapter 7 a little bit here. So anytime that I'm talking about a sample, kind of notice that things begin to get like little hats over them. And so the P hat is literally making reference to the fact that we're dealing with a sample proportion. So a sample proportion, again, is going to be that fraction looking thing of X over N. And again, X is going to be the number of individuals that in the sample actually meet a certain characteristics, and our little n there is the size of the sample itself. Majority of the time, this here, again, is not given as a beautiful fraction as this formula is written here. It is normally given as a percentage, or they will actually break it apart into two separate items. So they'll give you X and they'll give you the sample size itself. And we'll look at a couple of examples there. Now, this P item should sound a little familiar. And basically, when you talk about the means and standard deviations of a sampling distribution for a sample proportion, when we do this, this actually has to meet our conditions of kind of a binomial distribution. And what I mean by binomial is we saw that P previously before with the set number of trials as a binomial distribution. So again, we're getting that same item coming along here, except for now it's a proportion of the population, and we're not talking about how likely is this random individual item that I pull, or this random data value I pull, is going to meet this requirement of this distribution. I am literally saying, okay, I've already done all the beautiful stuff. I've now got this distribution. I'm going to pull something out of it as a sample out of the binomial distribution. And this is where this is coming from. So remind yourself by the central limit theorem, if something is already normalized, we still can use the normal distribution for the sample mean. But when it's starting off as binomial, there's some extra conditions that have to be met. And one of those is that basically in order for it to meet the first binomial condition in general, is that n times p has to be greater than or equal to 5, and n times the complement of p, which is 1 minus p, that actually has to also be greater than or equal to 5. If it meets that, that means the sample size is large enough to meet the binomial distribution rules, and therefore then we also can apply the central limit theorem as well if it again meets that sample of the original is actually large enough. Now with that, again, we've got some new terminology and new formulas that kind of come out. Again, if I am dealing with a proportion, our mean of that proportion that we're going to make reference to, so the mean of the p hat is going to just be whatever the population p is, and that's normally again given as a percentage, but the standard deviation is a little bit different than what we're used to seeing. So the standard deviation for this is p times 1 minus p, all divided by n, and all of that is underneath the square root. Now you definitely want to make sure to mark these down somewhere. These are very important, and again, make reference that this is going with a sample proportion. Okay, and again, p is making reference to the proportion of the population. P hat is making reference to the fact that we're talking about a sample proportion. Now, according to the central limit theorem, the standard score, the z-score for a sample proportion in a sampling distribution is given by the following formula. Again, it's still going to be our data value minus our mean divided by our standard deviation, except for now our data value is making reference to the sample proportion, so p hat, minus the mean of the sample proportion, which is just the population proportion there, divided by the standard deviation of the sample proportion, which again gets really complicated. Again, this is only needed if you are going to use the normal tables. And if you are using the calculator method, you don't actually need to do the z every single time, only if it specifically requires that. So it's not necessary. There's a lot of stuff that if you're doing it with the normal tables, that would allow you to do it without a calculator or a low-level calculator, but it involves a lot of extra formulas, okay? And you have to kind of remind yourself of this kind of switch up on the z thing. So I do want to tell it to you. I will show you how to do it with the tables again, but just keep in mind. Do keep in mind these basic symbolisms. So you're going to start to see the p hat, you're going to see p, you're going to see n, and I'm going to be looking for those in the problems. And these are the things I'm going to make note of. So let's just start with our very first one here. In a certain conservative precinct, 79% of voters are registered Republicans. What is the probability that in a random sample of 100 voters from this precinct, at least 68 of those voters would be registered Republicans? Okay. So first of all, kind of some key things so I make sure I know here. In a certain conservative precinct, 79% of the voters are registered Republicans. So that right there is making reference to a population, right? And then in the second part of this problem, it says, what is the probability that in a random sample of 100 that there's at least 68 voters will be Republican? Okay, so again, I'm not actually saying anything about a mean or a standard deviation. It's kind of making reference to some like probabilities or some percentage of something. So this is kind of what's giving me that it's a proportion idea here. So that's how I kind of know what I'm looking for. And so with that information that is given, we can see that p hat is actually going to be 68 over 100. They didn't actually tell me what the proportion was as a proportion. They gave it to me in two different items. They gave me the number of people with a certain characteristic and the size of that sample itself, which allows me to kind of look at that as 0.68 or 68%. Now, what I'm going to do is I'm going to sketch a normal curve because, again, my sample size is 100 here. And since my sample size is 100, the central limit theorem will apply. And we're going to look for the probability that at least 68% of those voters, again, are registered Republicans. Now, we need to actually find the area under the curve. And again, when I said at least 68%, that basically means I am looking for the area under the curve of that sample distribution that is to the right of 68%. Now, this value is a little bit smaller than the population proportion, which was 79%. And what we want to do when we are drawing these normal curves is, again, I kind of want to put in what the mean is. And again, this is the mean of the proportion here. So that's 0.79 instead of 79%. I'm going to actually use it as the decimal. I do see that 68%, which is 0.68, would be over here somewhere. So guys, if my answer is not bigger than 50%, because again, I'm shading everything from here to the right of it, because it has to be at least this or bigger. From here to here is 50%. So if my answer is not bigger than 50%, we've done something wrong. Now, to do this by hand, with the tables or with a very low level calculator, okay? And what I mean by low level is that it doesn't have the statistics side to the calculator itself. The first thing we need to do is we have to calculate that z-score, and to do that you need your p hat, which we found, which was 0.68. You're going to need your p, which is 0.79, and you need that n, which is 100. Okay, and so to calculate that z-score, we're going to use that data value of p hat minus the proportion of the population divided by the standard deviation of the proportion there. And that's, again, it's going to look really crazy as we start to do the math here, and it's approximately a negative 2.7. And again, it should be negative because remember we found it to be on the left side of the mean itself, of our mean of our proportion here. Okay, and I'm going to look always around 2 decimal places when I'm making reference to z's. We do 2 decimal places because that's what's on our table. Okay, and so to use the normal distribution tables, we're going to look on that table, look for a negative 2.7, and it should be approximately 0.9965. Now, the alternative method is to use your calculator, and it can be done in completely one step. So this is why if you were drawing your picture, it really did end up helping you out a little bit. So I drew my normal curve. I put on my 0.68, right? We also put our mean on there, which was 0.79, and I just wanted to make reference to it. But I also want to write down that I was going to have an n of 100, and I do also want to write down that which way am I shading, which was everything this direction here. Okay, so let's take a peek at this in the calculator and the method that we have to use. So in my calculator, I've got it up. Again, notice that we met the requirement for it to be normalized, so I'm going to hit second, bars, and number 2. Again, when I said that chapter 6, the normal distribution is probably one of the most important distributions, I was not kidding. We have 0.68 there as our lower bound. You can either say 0.68 or you can say 0.68. Either way will work there. We do see that our upper bound is a positive infinity, so 1e99. And remember, this e, it is not the, do not hit alpha e. If you hit alpha e, you're going to get it wrong. You actually have to hit second comma to get this e. This is a special e. It's a scientific notation e. Basically, this is one with 99 zeros after it. Okay, and then we're going to put in our proportion mean, which we said was 0.79. So we've got our 0.79 there in the middle. And then for our standard deviation, remember, this is the very crazy looking one. You're going to say second x squared to get that square root symbol. And then we're going to say our p-value, value, which was 0.79, times parentheses, and make sure you got parentheses here, 1 minus 0.79, close the parentheses. If you do not close the parentheses here, you're going to get it wrong. Divided by 100, and then close parentheses one more time. Okay, and paste it in. Again, you're still doing the exact same 4 steps that I was doing right there. For my TI 83ers, you just don't get that beautiful menu that actually has you write it all in there, okay? But you will get that exact same answer as well. And as you look at that, guys, there you go. That's everything that should be put in the calculator. And again, you're going to get that right answer, which is a 0.9965. Now, again, this is kind of why you do the little drawing here. And again, I did the drawing just to kind of help me out. Is it 100% needed? No, but it is very helpful. So basically, our answer to our question is the probability of having at least 68 voters in the sample of 100 being registered Republicans is approximately 0.9965. So the probability is about 99.65%. You will have at least 68 voters that meet that requirement of being a Republican, which kind of makes sense when you think about it, because the proportion of the population was 79%. So having at least 68, you're kind of still within that kind of range error. Let's try another problem. So in another precinct across town, the population is very different. Now in this precinct, 81% of the voters are registered Democrats. What is the probability that in a random sample of 100 voters from this precinct, no more than 80 of those voters will be registered Democrats? Okay. Now, the first thing I begin to notice is it gave me 81% based upon a population. So that is our P for our population. But if I have a population proportion, I need to have my P hat, which is my sample proportion. And my sample proportion is going to come from having that 80 out of 100. Okay, again, 100 is the sample size. 80 is how many meet the characteristics I'm looking for out of that sample. Okay, which means we have a 0.8 or 80%. Now, make note of the words. It says no more than 80 of the voters. So no more than 80%. So we're actually interested in that no more than 80% of the voters in the sample are actually registered Democrats. So what this means, if it says no more than, that means it can be that or less. I can't be bigger, no bigger than 80%. So I can be less than it, but not bigger. So this means all the area to the left of our 80%. And again, when you take a peek at that, our sample proportion is 80%. Our population proportion is 81%. So we should kind of mark that to see that it is slightly to the left of our sample, our population proportion. So it should look something like this. Now, once you've identified that, again, I'm not going to do the z-score method. I'm actually going to do the calculator method. Drawing the picture is really going to help me out because this allows me to identify what the lower bound is, what my upper bound is, and what my mean I'm going to be using, and what type of standard population or standard distribution I will be using. Ugh. Words are tripping me up there. Okay, so remind yourself, just to kind of give you guys a little bit of a helpful hint, this is always a negative infinity all the way out here, and this is always a positive infinity. But remember, I'm looking for everything from this 0.8 or my p hat, this is also known as our p hat here, and everything this direction, no more than, right? So my lower bound here is at negative infinity, my upper bound is where we got our p hat ends, okay? And then from there, we have our mean of our population proportion, which is 0.81. And then we have our standard deviation of the population, or of the sample proportion, which is going to be our really crazy looking formula down there, okay? And again, you kind of want to make note of this formula. It's really important to keep in mind. So again, steps in our calculator there. And let's see what we actually need to type in. So since there's nothing really special that I need to worry about because it's got a lower bound and upper bound, I'm just going to hit, I'm going to clear up my home screen and start fresh. So second vars, number 2 for our normal CDF. Now this time I said it was negative infinity. So I have -1 second comma to get our special E, 99. And then here we've got our nice lovely 0.80. And remember what our proportion there for the population, which was a 0.81. And then again, this is where it's going to go that really crazy extra step here. This is going to be the square root of 0.81 times parentheses 1 minus 0.81 divided by, and don't forget to close the parentheses on that, and then divided by 100. And again, it's 100 because that is the size of our sample itself. Paste it in there. And again, we get our beautiful answer. Okay. Now, the calculator is going to give the more accurate answer. It is actually better to use the calculator because it is more accurate. If you're using the z-tables, they are kind of pre-rounded before you even get to the table, which is why it's an approximation. When we always say it's approximation because we're going to end up rounding, but it's automatically pre-rounded when you're using the tables. And so the answers are slightly off, and just be aware of that. Okay, let's try this again. So again, the biggest thing is always just kind of keep looking for those key things in the problem. So it is estimated that 8.3% of all Americans have diabetes. Now suppose that a random sample of 74 Americans is taken. What is the probability that the proportion of people in the sample who are diabetic differ from the population proportion by less than 1%? Okay, so my keyword there that I kind of want to notice here is they didn't tell me how many successes out of my samples. So they just said that our sample size is 74. They also told me that this is the population's proportion that we're looking at here. But I want to know, what does the population, again, we're still doing what is the probability, but what is the probability that the proportion of people in the sample, so basically a sample proportion, differs from the actual population proportion by less than 1%. So this means that I'm going to basically add and subtract my 1%. Now remember, 1% as an actual decimal is our 0.01. So this here is actually, this is 1%. It's just normally, again, we write it as a decimal. And again, the population proportion, this here, writing it as a decimal, is going to be 0.08, because that's 8 cents, and then add my 3 at the end there. Okay, and so since we're differing from this, this is what we're adding and subtracting our 1% or 0.01. So we're interested in what is between this. So we've got what's between these two numbers, which is 0.073 and a 0.093. Again, next we need to identify that lower bound and upper bound, your mean and your standard deviation specific to this special problem here. And to do that, once you've got it done, you're going to use your calculator to do the rest of the problems. Okay, so again, as we're doing these problems, we do notice that in our case here, and I have a typo, that our P itself is going to be 0.083. That is our population proportion that was given to us in the problem. With our sample size on this one in particular, it was not a set number of what you're used to. It was like 74. Okay, so a little bit different than what we're kind of, not every problem is going to have perfect squares, so you got to keep that in mind. And then they told us kind of, again, what we've got our in-between items here. Okay, so, and then we've got our standard deviation that we've got for our proportion. So again, alternative method is going to be the calculator here. Now, as you guys were noticing on this one here, I basically said what's in between it. So really nice and easy here is that we are differing. So we're differing from our population proportion by 1%, and we're looking for what's in between here. So our lower bound is here and our upper bound is here. So as I do my calculator, again, it's all basically like one big step. You put your lower bound in, your upper bound in, your population's sample proportion mean there, and then you've got your standard deviation of that sample proportion. Okay, and again, as shown in this screenshot, this calculator method does give you a little bit more accurate of an answer versus the tables, which will be about 0.2448. Okay, let's try another one, because again, this is the best way to learn. So again, it is estimated that 8.3% of all Americans have diabetes. Again, we're going to suppose that we've now got a random sample of 91 Americans that is taken. what is the probability that the proportion of people in the sample who are diabetic differ from the mean by more than 2%? Now, this time it's a little bit different on my wording. Previously, I said less than 1%. This time I said more than 2%. So if I'm talking about more than, I'm talking about bigger than it. So by this one here, you're still going to take that population proportion and add and subtract your 2%. Again, I'm going to change these from percentages to decimals. And this is going to tell me my new numbers here, which is going to be a 0.063 and a 0.103. And again, because I use the word more than, with the word more than, that kind of tells me that I am going the tail parts of it. Now, with this one here, this is going to be a little bit different with using our calculator here, because in this case here, you notice I have a lower bound, an upper bound, and then I have another lower bound and another upper bound. You can either take this as the two different problems and add those answers together, or if we do this all in one step, I can actually find the complement area and then subtract that from 1. So that is really going to kind of help you out there if you do this alternative method. So with the alternative method, again, I'm going to start by clearing out my screen. I always like to start with a nice, beautiful, clear home screen and then say 1 minus, because again, we're doing this kind of alternative one-step calculator problem. And then we go to second vars, number 2, and then we've got our lower bound and our upper bound here. Now, remember what we did here was we basically took our sample proportion, population proportion, and we added and subtracted our 2%, which is again 0.02, and that's going to be our lower bound and our upper bound there. So you can either kind of do that in the calculator this way. It's going to look really crazy if you do it this way, so I do suggest take the time and actually do that subtraction first, and then that way you can just type in what the actual answer is itself and put in that 0.063. Okay, and again, doing the same thing the other way when you do that one, and you get that 0.103. Okay, and then for your mean on this, again, and remember it's the mean of the population proportion, which is going to be 0.083. Okay, and then for your standard deviation of the sample proportion here, again, if anything, start with a clean slate and go second square root, and then you've got your population proportion, P, parentheses, 1 minus that population proportions P, close parentheses, and then divide by this, the N, which in our case here was 91, okay? And then just be sure to click paste here. Now, I will say that you want to kind of be a little careful, you guys, because you always want to kind of close the parentheses. You'll notice I didn't really close the parentheses when I started, when I was doing this problem, so you kind of want to go ahead and do it and close it. If you've done that closed parentheses in the, for those of y'all that have the pop-up menu, it's really helpful. For those of y'all that don't, you just got to be super careful with the extra parentheses here, and just be sure to close them. Okay, and we get our answer. Again, this is going to be the more accurate idea here, which is going to be 0.4892. Okay, and again, it's probability, so we round 4 decimal places.